Okay, so we've developed an intuition about standard deviation and how to quantify the variation within a set. We built it around the car batteries, and we developed the need for every piece of the computation, right? The differences, the squares, the dividing by the number of batteries that we were looking at. So let's make sense now of the actual formula. So let's look at the formula we have here. And so much like the mean, you have to keep track of if you're talking about a population or a sample. And so if we're looking at a sample, we have this information here. This is the formula. Notice that even though this might look intimidating, this is what we did, right? We took every data value and and we subtracted the mean. Then we squared those. After we squared them, we added the differences and divided by n. This Greek symbol, it's the lowercase sigma. I'll even mention that here. That symbol is lowercase, it's pronounced sigma. So sigma squared is population variance. And then when you take the square root, you have standard deviation. Notice that this n down here, that is the population size, okay? Now when you look at sample standard deviation, things are slightly different. The computation is going to feel almost identical. Notice the change in notation. We're using S instead of sigma. Greek letters are typically reserved for population parameters. And then instead of subtracting our data value by the mean mu, we're subtracting by our sample mean. And then this denominator, n minus 1. Why n minus 1 and not n? Well, this is known as degrees of freedom. If I don't have the entire population, then there's no way for me to actually compute the true mean. But I could know all but one value, and I could engineer that last value to be whatever it would need to be, so that when I compute a mean, it's the actual true population mean. And so that's why we divide by n minus 1. It creates, it's unbiased, and it accounts for us not actually having the true mean when we make this computation. So let's practice this real quick. You've got a set of data here, and I want to go ahead and compute the sample standard deviation. How do I know it's sample? Well, it says sample, okay? So the first thing we need to do is get our hands on the mean. And so what I'm going to do that is I'm going to come out of here, and I am going to put this into Excel and add it up and find the mean. So if you want to go ahead and pause that or this, you might consider doing that. Okay, so I have my data in this column, and I'm going to write equals and then average parentheses and drag down here. And so I get a mean of 7.8. So let's come back over to the other slide here, PowerPoint slide. And we said that our mean was what, 7.8? So watch what I got here. Got a mean of 7.8. So what I want to do is I want to find, whoops, what I want to do is get this to write correctly. Let's try that again. I want to find the standard deviation. So S equals, I'm going to save some room here. So what I need to do is take 4 minus 7.8 squared plus 5 minus 7.8 squared all the way down to my very last value, 6 minus 7.8 squared. And then with all these, I want to add them, which I'm doing, right? Whatever that sum is, it's going to be divided by, well, let's see. This is a sample. What's the size? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So divided by 10 minus 1, or 9. Okay? And we could do that and then take the square root. And that very lengthy computation, with just a very tiny data set, frankly, would give us a standard deviation. I would encourage you to work that out. It's a valuable activity to get your hands dirty with the computation. But fortunately, we may also use Excel. And so let's come over here to Excel. And then I could do this by hand like I did, or not by hand, but I could do it in pieces like I did with the car batteries. Or why don't I just add a column here? Call this the mean. And then this, the standard deviation. And so again, I'm going to come over here. I'm going to say equals, and then Excel, we're going to write ST, and here it is, this one, STDEV dot S. And notice that there's also a P, that's for a population. This is for a sample. So the computer, Excel, doesn't know if I've given it population or sample data. So I'm going to choose this command for sample. I'm going to drag through those, and I'm going to get a standard deviation of 6.529. 6.529. And that's what this whole thing equals. Come back here. 6.529. Okay. Again, the mechanics of computing these things isn't the big point. The point is what these numbers mean. We know how to find the mean. Use Excel. Use whatever computational tools you have. We know how to find standard deviation. Use whatever computational tools you have. And then we're going to look at what those mean in the next sections. So until then.